Okay, thank you for giving me the opportunity to speak in this virtual conference in this challenging time. What I'd like to do today is talking about something that is related to very classical research on the mapping class group of a closed surface of GSG and give you maybe some new and different perspective about it. So we are interested in the mapping class group with some additional geometric structure. Mapping class group of a closed surface of genus G is a group of isotopic classes of orientation preserving diffeomorphisms of the surface. And such a mapping class may or may not preserve some additional structure, and the additional structure we are looking here is a spin structure on the surface. What is a spin structure? Classically, the spin structure on a surface is a covering of the unit tension bundle of the surface, which restricts to a standard covering of the fiber. Another way of understanding a spin structure is looking more directly on the surface and looking what such a covering of the unit tension bundle does to curves on the surface, or how it reflects to curves on the surface and cohomology classes. The following definition is due to Humphreys and Johnson. A spin structure on a compact surface S, where we allow boundary, is a Zim or 2Z valued function phi on isotopic classes of oriented simple closed curves on S, and such that the following two properties hold. First, we have twist linearity, which says the following. Let C and D be oriented simple closed curves, and let TC be the left Dehn twist about C. Such a left Dehn twist is defined as follows. You take the simple closed curve, you cut out a cylinder about the curve, and then a Dehn twist is a diffeomorphism which preserves the complement of the cylinder pointwise, preserves also, of course, the boundary of the cylinder pointwise, and twists one boundary component with respect to other one full turn. Then we can evaluate the spin structure on the image of a curve D under the Dehn twist about C. And the requirement is that this image is phi of TCD equal to phi of D, that means the image of the spin structure on the curve D, plus iota CD of phi of C, and taking modulo 2. So what is iota CD? Iota CD is the symplectic intersection form between the curve C and D. Since we are working here with Z mod 2Z coefficients, actually an orientation here is not relevant because every curve with both of its orientations defines the same homology class modulo 2. So we take here this homological intersection for modulo 2, and this is what the value of the spin structure is supposed to be on the image of E under the Dehn twist about C. There's normalization. We require that phi of theta is equal to 1 for the oriented boundary theta of an embedded disk in S. This is consistent with the definition that I gave before of a spin structure, because if you take an embedded disk, the boundary is of course homotopically trivial, but we can identify this boundary with a fiber of the unit tangent bundle over the midpoint of the disk by just taking, for example, the exponential map with respect to any given metric. And the requirement here is that this spin structure should evaluate to 1 on the fiber, which is reflected in the definition here. So saying that these two definitions coincide in the case of surfaces is the theorem of Humphreys and Johnson. But the way we think about the spin structure for the purpose of this talk is in the way Humphreys and Johnson defined it. And note that you can also define Z mod RZ spin structures on a surface for any R. And it is not too hard to see that such a spin structure can exist only if R divides the Euler characteristic. Now, if we have such a spin structure phi, then we can look at the spin mapping class group, which is a stabilizer of phi in the mapping class group. And since we are here working with finite data, the mod S phi, the stabilizer of the spin structure, is a subgroup of the mapping class group of finite index. So now one has to be a little bit careful about trying to understand the stabilizer of a spin structure, because there is an invariant. This invariant is defined as follows. You take a surface, again, a closed surface of genus G, then the RF invariant of a spin structure can be defined as follows. You take a symplectic geometric basis of the surface. This consists of 2G curves, simple closed curves on the surface with the following property. So we have A1, B1 to AG, BG, and we want that A1 and B1 intersect in a single point and are disjoint from AI, BI for I bigger than 1. And this is supposed to be holding true for all the other pairs here also. So that means AI, BI is disjoint from AJ, BJ if I is not equal to J, and AI, BI intersect in a single point. Then we can write down the following expression. So the RF invariant of phi is defined to be the sum over all I, phi of AI. So we evaluate the spin structure on AI plus 1. We multiply it with evaluation of the spin structure on BI plus 1. And of course, everything is taken in Z mod 2Z. Now, what one has to verify is that this invariant, the RF invariant, which is now a number which is either 1 or 0, because we're working here in Z mod 2Z, is defined independently of the choice of a geometric symplectic basis. That means if we change the symmetric geometric symplectic basis to some other geometric symplectic basis, then we obtain the same number. Now a spin structure phi is called even or odd if the RF invariant is 0 or 1. And now the question is, can one describe the spin mapping class group, that means the stabilizer of phi here, explicitly? And this is what I'm trying to convey to you, that in some sense this is possible. Now, if you look at this RF invariant, it may come as a surprise that this is relevant for understanding the spin structure, but it is a general fact that if you have two spin structures on the surface, then there is a diffeomorphism of the surface which pulls one spin structure back to the other one, if and only if they have the same parity. That means they're either both even or both odd. So now this means that even and odd spin structures are distinguished naturally if you look at invariance and the spin mapping class. So we have to take care of the parities in our discussion. Now, the mapping class group itself has many different known systems of generators. So there are many systems of generators that are given by de-interested but explicit sets of simple closed curves. The best known system of generators is probably the system that was introduced by Licorice. And this consists of 3D -1 simple closed curves, which I do not have here a picture now, but which are nicely spaced in the surface. That means any two such curves intersect at most one point, and they cut the surface into nice disks. There are some more easy to remember system of generators, which is due to Humphreys. It consists of exactly 2G plus 1 curves, simple closed curves. That means we take the de-interest about a system of exactly 2G plus 1 simple closed curves. And these simple closed curves also decompose the surface into disks. In fact, the Humphreys generators, the curves that define the Humphreys generators, are a subset of the curves that define the Licorice generators. It is also furthermore known that the mapping class group cannot be generated by 2G, by the interest about exactly 2G curves. And this has to do with the ORF invariant. Namely, if you take the interest about exactly 2G curves, then these curves have to generate the homology of the curved surface. That means the first homology. And such a system of generators always preserves this Z-mod-2Z spin structure. So the best we can hope for is getting the spin mapping class group. Now, let us look at the following system of curves on a surface. So I draw here a surface. Let me take this surface here that are given on the left-hand side. I draw here a system of curves. So you can see, so these dots are supposed to say that this system here, the surface can be extended in the same way. That means we add more of these handles circular about the middle hole if you want. And now the system of curves is as follows. We have here 2G plus 1 curves as well. So here, these are the curves that are 2G curves that go into these handles. And then there are 2G minus 1 because there's only one around the middle handle. And then there are two additional curves, which are these two curves that cut off this upper handle here from the rest of the surface. Now let us look at the right-hand side of the picture. Here we have also 2G plus 1 curves. So these are here a system of curves that are more reminiscent of the Humphreys generator. So they come here as the surface of genus 2, where we connect this to this middle piece here, this middle hole. And we have, again, as in the left-hand side picture, we have here curves that go out and decompose, cut the handle into pieces. And now there is one additional curve that is this curve. And you think about it, so we have this completely symmetric system of curves. And there's again two exceptional curves, that is this one and this one at the end. And these are like additional information, giving additional information, but I will explain this a little later on. Now, if you look at this system of curves, then the theorem is as follows. If we take an odd Z-mod-2Z spin structure on a closed surface of genus G bigger or equal than 3, then the spin mapping class group is generated by the interest about the curve from the curve system CG. Let me go back. So that means this system on the left-hand side corresponds to an odd spin structure. If we have an even Z-mod-2Z spin structure on a closed surface sigma G of genus now bigger or equal than 4, then the spin mapping class group is generated by the interest about the curves in the curve system VG. So let me go back. Let me go back here. So you can see here this is only meaningful if the genus is big enough. And so we have here, our restriction is here really for the right-hand side to be of genus at least 4. This is a version, so the version of this result is due to Calderon and Salter, who had a different system of generators for the spin mapping class group, starting in genus G4 to 5. You may wonder why the second statement only holds true for even spin structure on the surface of genus at least 4. You can prove that there is no system of interest that are nicely arranged by a simple closed curve that are nicely arranged in the way we have it arranged on the surface of genus 3, such that the interest about these curves define, preserve an even spin structure and generate a spin mapping class group. So in certain sense, this result is as good as it comes. And the motivation for this result comes from holomorphic differentials on surfaces in the search of understanding what's called the strata of abelian differentials. And so this is related, turns out to be related to the spin mapping class group and its structure. So in other words, this now looks as nice as it comes, as we know from the Humphreys generator. So now how would you proceed in proving such a result? The proof is also, in a certain sense, very classical. So you take the curve graph of the surface S, and the vertices are isotopic classes of simple closed curves, and edges connect to disjoint curves. This curve graph has been studied extensively in the past. It has very beautiful properties. And so many properties are known, and the most elementary property is it's actually connected. Now, what we want to do is we want to relate the spin structure to curves. And for that purpose, we look at the subgraph of the curve graph whose vertices are non-separating curves. And we also want that the phi evaluated on such a non-separating curve is equal to 1. So why is this a good way of defining a graph? Simply because phi of c is equal to 1 means that if we cut the surface open along phi, then we see a surface with two boundary components. And now phi of c equal to 1 on the boundary components means that we can attach a disk to each of these boundary components. And what we see here is a closed surface whose genus is less than the genus of the previous surface. But also the spin structure defines a new spin structure on this new surface, simply because this phi of c is equal to 1 is consistent with the requirement that the boundary of a disk has supposed to be the value of 1 under the respective phi. That is why we want exactly this definition. Now, there is a small worry about the parity. So this is, I just try to explain this to you. There's a small worry about the parity. The parity of the spin structure is preserved. That is not hard to check. And now what we have here is we have a way to do induction. And this is also the way a classical proofs go if you want to look at generators of the mapping class group of the surface. Then we try to proceed by induction. So that's our starting point. Now, the induction procedure is as follows. We fix such a curve in this graph CG1. Remember, this is a subgraph of the curve graph of simple closed curves which are non-separating and such that the spin structure evaluates to 1 on the curve. Now we use the induction hypothesis to generate the quotient of the stabilizer of C in the spin mapping class group by the point pushing group. So what is the point pushing group? The point pushing group is just the kernel of the stabilizer of C, now intersected with the spin mapping class group as I wrote in here, which is the kernel of the homomorphism, which is given by capping of the boundary and attaching this. That means the image of this homomorphism is the mapping class group of the surface of genus G-1. And here also we preserve this spin structure as an additional data. So of course the induction, the starting point of the induction is a matter to debate, and I will come back to it at the very end of my talk. But let us assume we have already a knowledge on the spin mapping class group for surfaces of a lower genus. Now we need to understand this kernel here, so the image or the intersection of the point pushing group with the spin mapping class group. The point pushing group is well understood. This is a classical Bellman exact sequence which tells you that the point pushing group is essentially, while we have here a non-separating curve, and so we have here two components. If we cut the surface open along C, we see here two boundary components. But so a slightly enhanced version of the Bellman exact sequence tells us that we understand the point pushing group in the ordinary mapping class group very well. But now what we have to understand is the intersection of this point pushing group with the spin mapping class group. And so if you do this, then we use this to show that this stabilizer of the curve C in the spin mapping class group acts transitively on the vertices of this enhanced curve graph or the subgraph of the curve graph with prescribed spin value, which are disjoint from C. So the stabilizer of this C intersected with the spin mapping class group clearly acts on the vertices or on the curve graph of all curves which with spin value 1, which are disjoint from C, and now we want that or show that this is transitive. The next step is to show that there exists an element in the mapping class group, the spin mapping class group, which maps C to a curve which is disjoint from D. That means that in such a way, if we have such an element, then we know that the stabilizer of C and the stabilizer of D are conjugate in the spin mapping class group. And now we have to show that this spin curve graph is connected, and we can use this to deduce that the following homomorphism is surjective. So we take the amalgamated free product of the stabilizer of C with the stabilizer of D, amalgamated of the intersection of the stabilizer of C with the stabilizer of D, and then the Sternald, the universal property of amalgamated products tells us that there is a homomorphism into the spin mapping class group. And all we want to show is that this is surjective, and then we can use our inductive knowledge to show that the spin mapping class group is generated in the way we are. So what we then get at the end is, in an inductive procedure, that the mapping class group, the spin mapping class group, is generated by the Dane twist about the curve from some enlarged system. Here I only look at the case of odd spin structure. Even spin structure is done in the same way. This enlarged system has additional curves. So the original system had the D1 and the D2 that you see here, but not D3, D4, and so on. And then what we do is, in the final step, we show that the Dane twist about the curves from this curve system SG minus the original curve system CG can be written as words in the Dane twist about the curves from CG. And then we are done. Now, why is this? Well, there's a 1 missing, sorry. Then why is this CG connected, this CG1 connected? Here's a proposition. If G is equal to 2, and if the spin structure is odd, then this graph here doesn't even have any edges. So it is a little bit not obvious whether or not this graph CG1 is connected in the case that the genus is at least 3. Now here's a trick that is due to Putman to show that such a graph is connected. Namely, we take a graph with a vertex transitive action of a finally generated group gamma. We take S a finite generating set for gamma, and if there exists some vertex V in G such that for every G in S, the vertex V is connected to GV by an edge path, then the graph is connected. That is a very nice trick, because it is an easy mechanism to show that the graph is connected, but we need to have an understanding of a vertex transitive action, and we also have to have this generating set. And now you realize that you are a little bit in trouble simply because the mapping class group, or the full mapping class group, does not act on CG1, and we want to use connectedness of CG1 to find generators for the spin mapping class group. However, there is a little trick. We can use the Putman trick to produce connectedness of other graphs and use that to show connectedness of CG1. This goes as follows. We define the graph of non-separating pairs to be the graph in S, whose vertices are now pairs of curves in the curve graph, so there's no spin value here associated to it, such that the complement of C union G in S is connected. Then two vertices are connected by an edge, so that's a definition. So we have vertices are pairs. C1 D1 and C2 D2 are connected by an edge if, by definition, C1 is equal to C2 and D2 is disjoint from D1. And now the Putman trick tells us, because now the mapping class group acts on this graph, that this graph is connected. And this is not hard to show using the explicit knowledge of generators for the mapping class group. And of course, here we require that the genus is at least 3. This graph doesn't make any sense for genus equal to 3. And now the idea is to associate to a pair in this new graph in a non-deterministic way a curve in our graph CG1 and construct an edge path between lambda of C1 D1 and lambda of C2 D2 for any two adjacent vertices C1 D1 and C2 D2. That means this allows us to simplify our problem of showing connectedness to some explicit configuration where we have a lot of control. So what is the definition in our setting? The definition is as follows. We take lambda CD is equal to C or D. So this is not deterministic, that means we make choices. If either phi of C is equal to 1 or phi of D is equal to 1. So if one of the two has value 1, we pick one of the two which has value 1 and uses as a definition of lambda of CD. And if phi of C is equal to phi of D is equal to 0, then we choose an arc connecting C to D and let lambda CD to be the boundary of a tubular neighborhood of the union of C and D and this arc. And this is not hard to show that the value of this new curve is actually 1, the spin value of this new curve is actually 1, and that furthermore, we know that this curve is non-separating because of this requirement that S minus the surface minus the union of C and D is connected. And so if we make this definition, then we can sort of hop from vertices to vertices in this graph NS, use the connectedness of this graph N of S to produce between any 2 points in the graph CG1 connecting. So now, what is the outlook of this? I explained before that the reason why I got interested in this question about finding generators for spin mapping class group had a priori nothing to do with the mapping class group, but it had to do with the, trying to understand strata of abelian differentials on closed surfaces. Now, we can make the following definition. What are nice curved systems on our surface S? We define a curved system C on S to be admissible if any two curves from the curve system C intersect in at most one point, if the complement of S minus C is a union of disk, and if the curve diagram of C is a tree. So what is the curve diagram of C? The curve diagram of C is defined to be the following finite graph. We take as vertices the curves in our system, and we connect any two vertices by an edge if and only if they are intersect. And then if they intersect in exactly one. Let me go slightly back and look at our this system of curves. The curve diagram, this is an admissible curve system. The curve diagram is a tree because here you have vertices, so the tree looks like follows. You have one center vertex. You have going out of the center vertex are going paths. And so there is an alternating between paths that has length 2, namely consisting of two edges that are connected. So that's a line segment of length 2, and then comes just a line segment, so that's just an edge. And then here comes more a line segment of another line segment of length 2 and another edge. So that is clearly an admissible curve system. And now the theorem is as follows. The subgroup of the mapping class group generated by the Dehn twist about the curves of an admissible curve system is either hyperelliptic. Hyperelliptic means it defines a hyperelliptic, so it commutes with a hyperelliptic involution, which is a special case and can be easily checked, or it is a stabilizer of an explicit Z-mod RZ spin structure on this. So that means no matter what we draw on the surface, we can identify immediately, provided that we draw an admissible curve system, we can identify immediately the subgroup of the mapping class group generated by the Dehn twist about this curve system. And so here, how do we find this R-spin structure? So we have to check parity, even or odd, which is a matter of checking. So one has to sort of train oneself to see whether you get an even or odd spin structure. But now, how do we detect that this defines the Zimmer-Tusi spin structure? Here there's a complementary region that has small complexity. That means so I can only add one more curve in this complementary region, which is disjoint from all these. So in other words, I cut my surface open along these two curves, and I try to add more curves to my admissible curve system. So that means I add a curve that intersects one of these additional curves by in at most one point. And now you can see that in this configuration here, you can add one more curve, but that's it. So then you are done. So this can be described completely combinatorial in terms of the number of vertices of the polygons that are obtained by cutting your surface open along this curve system. And now in this particular case, since the number of vertices here is now hopefully 8. Hopefully that is not right. But then you see that you get a Z-2Z spin structure. If you have larger polygons, that means, for example, if you, let me go back here to my previous picture, which is a little bit easier to see. So for example, if you take this picture, if you move this, if you take this curve out and move it on top, then the group generated by this game twisted about those curves is a full mapping class group. If you take this over here, then it preserves the Z-mod these 3Z spin structure. So in other words, you can explicitly detect what kind of subgroup of the mapping class group you obtain. Thank you very much for your attention.